Hey everyone, welcome to the AI show. Good Monday morning, evening, afternoon, depending on where you're coming from. Thank you so much for joining me today. We have a great show for you today. We are going to be learning about on-device training. So first though, we love to start out, tell me where you're from, say hello. It's so cool to see all the people that join us for these shows. I am in Minnesota, which if you've tuned in before, you know. And you may notice that I'm not Seth. Seth is on some much deserved vacation, so I am hosting for him. And yeah, see, no one's telling me where they're from yet. Hey, Tim, welcome. Get your questions ready too, because after we do the demo and talk about how on-device training works with ONNX Runtime, Banji is going to be joining with us, and he is going to be here to answer all of your questions on how to do on-device training. All right, there we go. So we have Simon from Vancouver, the land of the cool. Cool isn't cold, or cool is too cool for school? Do people even think? People don't say that anymore, do they? I'm old. Okay, and then, ooh, Jersey, hello, welcome. Got Colombia. I got to get my music figured out. I don't have it all set up. Seth has a really cool soundboard. That's how he plays his music. And I need to reset mine up so I have some good music when we do these. All right. Well, without further ado, let's take a look at how we can start doing on-device training with ONNX Runtime. Hey everyone, you're not going to want to miss this episode of the AI show where we are going to be talking to Beju from the ONNX Runtime team, and he's going to show us how we can start doing on-device training with the ONNX Runtime engine. Let's jump in. We are joined by Beju. Thank you so much for being here. Why don't you tell us a little bit about who you are and what you do at Microsoft?
Hey, Cassie, it's great to be on this show with you. Thanks for having me. I'm Beju. I'm part of the ONNX Runtime team, specifically working on training. Most people think of ONNX Runtime as an inference accelerator and know about its cross-platform compatibilities. But very few know that ONNX Runtime also supports training workloads and accelerates training scenarios for a large variety of models. Yeah, so I'm part of the ONNX Runtime training group, and I'm here to talk about on-device training.
That's cool. So I'm excited to get to talk to maybe about some of the less known and newer features within ONNX Runtime. So there's accelerating for training, you know, with like large transformer models. But now we're going to be looking at more of the smaller models that you can run on device. And there's a lot of benefits to doing on-device training. But if you don't know what it is, why don't you, can you tell me a little bit about what on-device training is?
Yeah, sure. So on-device training refers to having the ability to train deep learning models on devices, on edge devices, such as mobile phones, gaming consoles, or even web browsers. And over the past few months, our training group at Microsoft ONNX Runtime team has been working hard to add this capability to train deep learning models on edge devices. And that's what on-device training is all about.
That's cool. And like the benefits of like the cost savings for running on device, the data privacy because the data never leaves the device. The updated model also stays on the device, right? There is ways I think to kind of push that stuff off the device when you need to, but the latency, right? It's better for latency for on device as well because you're not making any calls out. And then the limitations are all obviously like the hardware size and how to optimize for that.
Yeah. So for this show, I've prepared a demo that walks us through how we can start from a forward-only ONNX model and go all the way to deploying the models on the Android application, and doing the local training there. So in this demo, we'll be using the transfer learning capabilities. We'll be starting with the MobileNet V2 model in PyTorch, exporting it to ONNX, creating the training artifacts. And this Jupyter notebook leverages all of these steps that I just mentioned. And we'll walk through them one at a time. So to begin with, we pull the MobileNet V2 model from PyTorch and export it to ONNX, keeping in mind that we're moving from 1,000 classes at the output to just 4, because in our scenario, we're going to do image classification with 4 classes, with 4 labels. And so, as you can see, the first step is exporting the model to PyTorch, to ONNX from PyTorch. And this should create an ONNX model in the training artifacts directory. Okay, there we go. So this created the MobileNet V2 model. Okay, so here's the forward-only ONNX model. As you can imagine, this is the MobileNet V2 model. So it has a bunch of convolution layers, and the final classifier layer, which is gem, has 4 labels associated with them. And for the purpose of this demo, we're just going to be training the last layer, the classifier layer. So the rest of the model weights remain intact. Only the last layer model parameters will be learned or trained, so to speak.
So we're able to just grab this pre-trained model, open source, from the Torch Vision API. And then now we have that, and that's our base model that you've exported. And now we're just going to be able to update that last layer with our local device on training. That's kind of the high level of what you just did.
Yeah, that's right. We're just going to we will be training the last layer and keeping all the remaining model parameters intact.
All right, cool.
So now that we have the forward-only ONNX model, it's time to create the training artifacts. And so for that, we have the ONNX runtime.training.artifacts utility that helps us do this. The first thing is we're going to load the forward-only ONNX model that was stored in the training artifacts repository, define the parameters that requires gradient computation. That's going to be the last layer's weight and bias. So, and all the other parameters are going to be frozen or constant, so to speak. They will not be updated while the training happens on the device. With those parameters, those variables set, we can call artifacts to generate artifacts, provide the ONNX model, provide the requires gradient parameter, frozen params. And for the purpose of this model, we're going to use the softmax cross entropy loss function. We're going to use the AdamW optimizer, and we're going to save all these artifacts to the same training artifacts repository. And when we run this cell, that should generate all the necessary models or the artifacts in the training artifacts repository. So we'll walk through each of them one at a time. So first, let's look at the eval model. The eval model is basically the same as the forward-only ONNX model, except for the fact that the last layer has a loss attached to it, which is the softmax cross entropy loss. But the remainder of the model remains exactly the same. Next, let's look at the training model. So the training model is very similar to the loss model, with the distinction that after the loss, we have the gradient graph for the classifier weight and classifier bias. So this is the gradient graph attached to the eval model, and that defines the training model. The optimizer model is a very simple one. It takes in the parameters and the gradients and updates the gradients in the direction of updates the parameters in the direction of the gradients. And this is the learning process in the on-device training. And finally, we have the checkpoint folder, which encompasses all the model parameters, trainable as well as non-trainable, so that they are not embedded within the ONNX model. So they are shared across the training model and the eval model. These will be the 4 training artifacts that we will need to deploy to the device, to, in our case, the Android application for on-device training. So those are kind of the high-level steps that you need to do. Now, when it comes to choosing the loss function and the optimizer, that type of stuff, those are things people can kind of play around with to see what they need for their scenarios, right? But there kind of tends to be, like, these are probably the more widely used ones for this type of task, right? So these are customizable. Users can attach a loss function of their liking. We offer a few out of the box, but if the user wants to, if the developer wants to define their own custom loss function, they can do so and just provide that as an argument to this function.
Okay, so these artifacts are part of the ONNX Runtime library that you're setting here?
Yes, exactly. All of this is part of the ONNX Runtime training library.
Cool. So now we're ready to actually see how we take this and do the training in the application itself, right?
Yeah. So now with these artifacts generated, we are ready to perform training. Before we go into the Android application, let's just see if we can actually train using these artifacts and prove that uh, this kind of transfer learning is possible on the mobile NetV2 model. And so we will do this experimentation in Python. As I mentioned before, ONNX Runtime training offers Python bindings in addition to other language bindings, so that we can test out our solution on our local machine before we actually go into writing the application. And so we have this another a Jupyter notebook called train, which takes these assets that we developed and that we generated in the previous step and learns to classify animals. In our case, learns to classify between dog, cat, elephant, and cow. And so the process is really simple. We do some pre-processing, again, some more pre-processing, define the number of epochs and the samples for each class. As you can see, we only need 20 examples for each class, and we run it for 5 epochs. And here is where we interface with ONNX Runtime's training API. So we import ONNX Runtime.train.api, and there are 3 important classes that the training API exposes. The first is the checkpoint state. The next is the module, and the last is the optimizer. The checkpoint state can load the checkpoint artifact that was generated earlier and loads all the module parameters defined within that checkpoint artifact. The module class takes in the training model, the checkpoint state that we just created, and the eval model, and will be responsible for orchestrating the training. So functions like train step, resetting the gradients will be exposed through the module class. And finally, the optimizer takes in the optimizer model and is responsible for exposing functions such as optimizer step, which essentially means updating the model parameters in the direction of the gradient. As you can see, the optimizer takes in the optimizer model as well as the module that we just created here. After setting up these 3 variables, these 3 objects, we can define our training loop. And over here, we iterate over 5 epochs, and within each epoch, we run through 20 examples per class and run the model. So we compute the training loss by providing the input images and the labels to the model. We take the gradient step or the optimizer step and then reset the gradients for the next computation. And we can run this. And at the end of each epoch, I'm outputting the loss, the training loss.
So now this is the logic that we need to take those assets that we created and actually run that training loop. And now we're doing it in a Python notebook, but this is going to be the same steps you would follow for implementation in any of the supported languages, right?
That's right. This is a proof of concept showing that training is possible with our artifacts. It's a way to expedite experimentation. So instead of doing all the experimentation on the device application, we do it offline to prove that such training is possible. And then once we have our experimentation done, we can just port over our what we've done in Python to the application. So in this example, the Android application. And as you can see, after each epoch, we have the loss going, the training loss decreasing.
Mm-hmm. And this could also be used then for them to figure out what the right amount of epochs and sample images and that type of thing for their scenario, trying maybe different loss functions, things like that. So this is like our development loop for building our model and how our model is going to learn on our device.
That's right. All the hyperparameters, loss function, the learning rate, and anything that is specific to the training scenario, training solution for our users can be experimented with in this offline phase before actually going to the application development phase.
Great.
Cool. So now that we have a trained model, the next step is how do we know whether this model works in the real world? And for that, we expose a functionality, which is exporting the training artifacts for inferencing. So given a trained model, we can export that trained model to an inference-ready ONNX model. And then after doing that, we just load up this inference ONNX model with the existing ONNX Runtime inference session and perform inferencing with that. And okay, so here, after setting up the inference session, I can run a quick test to make sure that our model works well. So as you can see, the input image that I provided is one of a dog. and our model predicted with 61% accuracy that it is a dog. So it seems like we can actually use the MobileNet V2 model, the pre-trained model, only update the last layer so that we relearn the parameters in the last layer to use it for an application of our choosing, to classify images of labels of our choosing.
Okay, so we saw how you were able to do on-device training with your customized images and get this response. How does that compare to the accuracy of the model without any additional training? Like, how is it performing before we did this additional step?
Okay, so yeah, that's a good question. So we can just basically load the original ONNX model and test out whether the original ONNX model performs well or not. So here I've just copied over the same block as earlier, with the one difference is that instead of loading the training model exported to inference model in the inference session, I'm going to load the original ONNX model. So you can see over here, I'm loading the training artifacts MobileNet V2 model. So this is the original forward-only ONNX model.
Okay.
And then, so let's run this. And then if we call predict on the same test image, we can see that it gives random accuracies for each of the 4 classes. Mm-hmm. And in this case, it actually predicts that the given image is that of an elephant.
So yeah, we got a lot better results. I mean, it's kind of an elephant, not really. Maybe if it had a little bit longer trunk, I think, but it's definitely a dog. Okay, cool. So that really showcased nicely the power of just a little bit of extra training on some customized or on some images, custom image sets to improve the performance with on-device training.
Yeah, so I think at this point we've showcased that we can actually use the MobileNet V2 model, fine-tune it for our needs, and learn to classify images of any classes that we really want to do, that we want to really classify. Now we can extend this application and learn to even classify images of ourselves, for example. So we could learn to distinguish Cassie from Beju, for example. And I think the Android application will strive to do that. So let's just try to see how we can do that in the Android application. Yeah, so here I've opened up Android Studio and loaded the code that's available in the ONNX Runtime Training Examples repository. Also note how I've copied over the assets that we created previously in the offline Python script and added them to our assets folder in the Android application. Just head over to the 2 important functions in this application. The first one being training. So so here I defined the training loop again, and it's pretty much the same as the one that we defined in the Python script. The number of epochs are 5, and batch size is 4. So we process 4 images at a time, so yeah, we loop over the number of epochs and our input data. We do some pre-processing, and then we call perform training. And this is where we interface with ONNX Runtime. So we go into this ORT trainer class and look at perform training. The first thing to note is the constructor. We create the ORT environment using ORT environment.get environment. We create the training session using the environment that we just created. So ORT env.create training session, provide the necessary checkpoint paths, training model paths, evaluation model paths, and optimizer model paths. And now we're ready to perform training. So this perform training function creates the input ONNX values, so the input tensors for training that are that can be comprehended by ONNX Runtime. And we call ORT training session.train step and provide the inputs to that. The inputs are going to be the image data and the labels associated with those image data images. And we can get the training loss as output from this train step call. So after getting the training loss, we can call training session.optimize the step and training session.lazy reset grad, which will reset the gradients. So as you can see, this is pretty much similar to the way we defined the training loop in Python. And the other function of interest is the perform inference one. So here, what we do is once we've completed training the model, if we create the inference ready ONNX model from the trained model. So we call ORT training session.export model for inferencing, provide the model path where we want to save the inference model to, and we are ready. And this will generate the inference ready ONNX model. And that's pretty much it. That's how we interface with ONNX Runtime.
That's cool. And I think that anyone's probably worked, if you've worked with like image classification, this all looks really super familiar. And if you've worked with ONNX Runtime inference sessions, even that having the training session, but it's still following a lot of the same, the like, things that you would expect, the steps that you would expect to happen.
Yeah.
Now, I said you went straight from like, you created your inference model and then you created your session. Is that model saved? Like, is it output to the device too? Or
Yes.
are you just doing that all in memory?
So currently this will output it to a file location on the device.
Okay.
But we are preparing a solution where instead of only outputting to a file, we can also get it in memory. So that's not available yet, but we are working on that.
What are the kind of device requirements for running training? Will it run on anything as long as there's enough memory to do it? Is there, or I guess, how are the constraints around local training considered within the training API?
Pretty much on-device training will work for any device that our ONNX Runtime inference solution works on. The only limitation is that you don't want to train at a time when the user is probably interacting with the device. So you don't want to slow their functionality or impact their the device functionality in any way. So you would probably train during idle times, when the device is plugged into a charger, or at night when there isn't much activity on the device. But the ONNX Runtime training on-device training solution should just work for any Android application or any Android device that our ONNX Runtime inference session works for. Inference library works for, yeah.
Cool, that's awesome. All right, I think I have a good idea of how we now can take the logic and implement it into a Java application. Would be really similar with the other APIs that are supported, like C#, soon to be JavaScript as well, with the ORT web. But I would love to see this work on the Android, and I think you have a demo of this working, right?
Yeah, so let's just jump into the demo. So for this demo, we're going to learn to classify images of 4 popular celebrities: Tom Cruise, Brad Pitt, Ryan Reynolds, and Leonardo DiCaprio. So as I mentioned earlier, we can use the same transfer learning technique and learn to classify images of custom classes. And over here, I'm doing that with celebrities. Now you can see that I'm actually trying to predict the celebrities, but it got it wrong on the test images that I provided it. That's because we've not yet started the training process. And now we're feeding in images for each class. We're feeding in 4 images, or 16 images per class for Tom, Brad, Ryan, and Leo. And we start the training process. In the training process, we are looping over these 16 images per class for 5 epochs. And at the same time, doing all the pre-processing and post-processing and all of that. And now we are ready to perform the inference. You can see that after exporting to inference, we can actually learn to predict the celebrities correctly.
So for people that were watching and really want to get started and try this out, where can they go to learn more?
So I think ONNXRuntime.ai has a really good getting started page. It links to our blog, which goes into depth into our architecture. So it has a link to this current blog that I'm over. It kind of explains the trade-offs, the benefits of on-device training, and when to use it. It also has some instructions on how to get started with the different language bindings, how to install the libraries, and also has a link to the tutorial demo that we presented today. So I think that would be a good place to start.
Awesome. So we got everything you need on that link that we're showing below. You can go there, read the blog to get a more detailed look at what we were showing you. There's those examples on the GitHub. Lots of ways to get started with this. And again, Beju, thank you so much for joining today and showing us these really neat features for how to train on device in ONNX Runtime.
Thank you, Cassie.
All right, we went over a lot of cool information there on how we can start training on device. Now I'm going to welcome Beju, who is here to answer your questions. So thank you for hanging out with us today.
Thank you, Cassie.
Okay, so there was a lot of information there on how to do training with ONNX Runtime. We gave a doc link so people can go try it. We actually had some interesting questions in here because I think that when, you and I have worked with ONNX and ONNX Runtime so much, sometimes we read the basics of what is ONNX. So let's start with that, because somebody was asking about this, and I think this is such a good question. They're saying, what is the ONNX framework, and does it convert to a specific format?
Yeah. So the way I like to think of ONNX is it's a way to define a deep learning graph. Um, it's a format with some rules that help us define what the graph structure should look like. And this format is what is called as ONNX format. And we have a few uh, utilities available to export models from the original framework, for example, PyTorch or TensorFlow, even scikit-learn to ONNX format. And this ONNX format is basically a graph definition, which can be loaded at runtime on a runtime engine such as ONNX Runtime.
Exactly. So it gives us this file format that makes our model able to be run in multiple languages. And this really exchange, and this actually stands for Open Neural Network Exchange, is what ONNX stands for. And the way that I think about it, if you're a traditional developer out there and you're new to machine learning or you don't do a lot of it, I think of it as like in C# you compile your program down to a DLL. Well, in machine learning, you train your model and you export it to an ONNX file, and that's what you can take and then use different places, right? So like to really oversimplify it at a way, if someone doesn't know what a machine learning graph is, that's kind of the way you can think about it. And then so that once you get that ONNX model, then you can do all these different things with it. So in the on-device training, we exported 4 different models, graphs, the evaluation, the training, what was it? The model
The
itself, and
optimizer.
then what's that? And
So training model, evaluation model, optimizer model, and the last one is not really an ONNX model. It's a checkpoint
the
file.
checkpoint.
Yeah.
Right. So those are the 4 assets that we needed, and we were able to leverage ONNX in order to do that. And then now that they're in that ONNX format, we can use the ONNX Runtime API to use whatever language we want, which someone was asking about Rust. And I know, wasn't Rust added recently, the support for that with ONNX Runtime?
So the support for Rust has been added to ONNX Runtime inference framework.
Okay.
But we haven't added that yet for the training framework. There was some interest in adding the Rust bindings, and I think from our perspective, we can pick this up on a need basis. And if there's a lot of interest, we can surely work on that. But as of now, the training API do not have Rust bindings.
Great. And now we saw a computer vision task. What other tasks, do you have examples for other types of on-device training, or is it mainly just image classification right now?
So we have a few examples in our GitHub repository for text, for language models
Okay.
that run on device. And we have a super cool project that we are currently working on. And I think there's a pull request out for it already, which uses the wave to vec model to perform speech classification. So it tells whether or not the speech was mine, and that's pretty cool. It's going to be an iOS project, and the pull request is out. I think it should be more soon. So we have a few examples. We also have a basic getting started MNIST example. So if you're interested in just learning our API, that would be, I guess, the best place to start.
Great. So lots of examples out there. And then for the speech classification, are you using Whisper Tiny as the base model, or?
I could be mistaken, but from what I remember, it's the wave to vec model.
Okay.
Yeah.
Cool. Any other questions that anyone has about on-device training or ONNX Runtime or anything like that? We're happy to answer all of those. I know we were talking about training this time, but there's so many features within the ONNX ecosystem, I guess is what we could call it, right?
Yep.
Let's see. I don't see any other questions coming in yet. Anything else you want to tell us about the new training? Maybe that we didn't cover, or did we kind of cover it all the basics? Did we?
Yeah, I think we got all the basics in. I can probably plug in some of the work that we are currently doing. So right now for on-device training, we're working on the iOS package. So soon you'll be able to perform on-device training even on iOS applications. Um, we're also working on providing the ability to perform on-device training through web browsers through our JavaScript bindings. So that's something to look out for as well. Um, yeah, and and one more thing that we've recently added support for is the ability to add the pre and post processing ops within the ONNX model from the ONNX Runtime extensions library or from a user's custom library. Um, with that, we can do a lot of pre and post processing within the ONNX Runtime ecosystem as opposed to doing it outside.
I love ONNX Runtime extensions. And if people haven't checked it out yet, it's super convenient for when you're trying to take a machine learning model and run it in different languages. So for like different C# applications I've done for machine learning, I think I've leveraged ORT extensions in probably every single one for tokenization and pre and post all the pre and post processing that needs to happen. There's a lot of logic. Like even when you were showing your computer vision one, you were kind of saying, you know, here's my pre and post processing. When you start moving those to different languages, you have to re-implement that.
Yeah.
And one of the really cool things is with the ONNX ONNX Runtime extensions, you can actually put that right into the graphic itself. So you get one asset, like with your model, your pre and post, and then that makes your implementation code for different languages much less. So that's cool to see. I also, you mentioned ORT web. That will be really neat to see what people do with that for on-device training.
Yeah, and then the last thing that we're currently working on is, or we already have a solution for it, is basically providing a way for users to create that minimal build for users who have a very restrictive application, very restrictive resources on the application. We can really lower your binary size down quite a bit. So you don't pay the penalty of the application size bloating up because of using ONNX Runtime or on-device training with ONNX Runtime. So yeah, that's another feature that we've recently added.
Well, okay, so we have a question here. It says, what's the difference between MLflow and ONNX models? Also, both aim to improve interpretability, but ONNX appears to be more for deep learning. Is that accurate?
I would say that I'm not very familiar with MLflow yet. Probably I should look it up. But I think from what I remember of MLflow, from the basics I know, ONNX offers a way to go cross-platform, perform training, inference, and provides a large number of language bindings. And it's actually meant for production scenarios without the need to plug in Python for inference or training. So I would say for production scenarios, probably ONNX is the format to pick. But I'll let you pitch in, Cassie. I'm not very familiar with what MLflow offers yet.
Yeah, and I don't know much about MLflow either. I haven't used it much. So I'm like pulling up the documentation and like, let me read more about it. But I think MLflow isn't it just Python? I don't know if it supports other languages.
I thought it was, but I'm not really sure.
Yeah, so sorry, we can't really do a good comparisons, I guess, because neither of us are super familiar. But like as I'm reading here, it says it's an open source platform for machine learning lifecycle, and I thought it was more like an MLOps tool. So it's like tracking models and registry. So I feel like this is more. And that's kind of what I thought as I'm reading through this. But I wanted to confirm that it's more like seems to be like an MLOps model deployment framework for different model versioning. And again, I could be wrong. I'm just looking at the documents, and that's what I've heard it be used about. Like when I've heard people talking about using it, it's more in that framework. So I didn't know if they do have their own format, like model format. That's news to me. I didn't know about that. So yeah, I think they have different. I would say that they probably have very different use cases. You'd probably use an ONNX model in your MLflow process, right? And you might even use ONNX Runtime as your runtime within MLflow MLOps process. That would be kind of my understanding of how MLflow. But like again, it looks like they do have different bindings. So they have a Python, R, Java, and REST API. Well, REST API for So Java and R. And yeah. But yeah, I think they're kind of different uses, but that would be kind of my non-expertise for that MLflow perspective, just by looking at their document quick and kind of confirming what I have heard. So good question. I think that's all the questions we have. Oh, I was going to ask about federated learning. So we saw that we trained the model, we had it outputted to device. Can you tell us a little bit about what that is and how people use it and if it's supported in this?
Yeah, so federated learning is so typically for on-device training we have two scenarios that we like to think of. One is the personalization that happens on the device. So you learn to you train the model on the device and then you perform inference on the device from the locally trained model. So that's what we call as personalization. And the other scenario that we often like to think about is federated learning, which is basically these models are deployed on a plethora of applications and devices. Each device locally trains the model to some extent, creates the local gradients, and sends these local gradients up to a server where they are aggregated and redeployed to these devices, to these plethora of devices all across. So it's a the way I like to think of it is it's like a decentralized training process, and allows users to allows devs to train a model globally with local user data that doesn't leave the device at all. So you train locally on the device, and respect the privacy of users. So you don't send any data to the servers. You train locally. You only send the differences or the gradients to the central server, which aggregates the model again, redeploys the model, and this process continues over and over again. Um, and yeah, so that's what a little bit of federated learning. And the good news is that ONNX Runtime currently does support federated learning with on-device training. So what you would do in this case is instead of exporting the model for inferencing on the device, you would get the model parameter buffer, which is basically encapsulates all the model parameters after the training process. Once you have this buffer, you can perform some kind of encryption or differential privacy as required by your application. Send it to the server where it can be aggregated, loaded onto the model, or redeployed or to be loaded onto the devices for the next round of training. Yeah, this is already available on device training with ONNX Runtime.
That's great. That is awesome. So it's already supported. You could start using it now. And it's such a cool way to kind of continually improve your machine learning model with the user data while still protecting their privacy for the data that's being used to train. Okay, so we have another question. Let's see. I don't really know the answer to this one. Maybe you do. What are other ML frameworks runtimes out there that support on-device federated training?
I'm not really sure about federated training, but I know that TensorFlow Lite has some support for on-device training. I don't know to what extent that support is right now. And I do believe there was some project within the Torch ecosystem as well to perform on-device training. But yeah, and those are the only two popular frameworks that I can think of at the top of my head right now that have some form of on-device training.
Yeah, I think is it kind of newer or getting more popular now? I feel like I get a lot of questions around on-device training more recently.
I think it's not a relatively new field, so it's been around for a while. What's reshaping this scenario is that hardware companies wanting to, and rightly so, restrict and the users as well, wanting to restrict the data that they want to share to the servers. And so, in a way, this approach kind of respects user privacy, security, and so users feel more secure. And I think that's the trend going forward. So on-device training probably will be a way for us to be able to train models without really impacting users' privacy.
Yeah, That makes a lot of sense. And if you think about just tech in general, the decentralization things that are coming through for data privacy, it makes sense that machine learning is also looking at, and those types of uses are becoming more popular and more mainstream. So it's great to see that support within ONNX Runtime, within the different language bindings and that kind of forward movement. So I don't think we have any other questions here. Last chance, everyone. Thank you so much for joining us and answering all of our questions and telling us more about this new feature with ONNX Runtime. I'm excited to go try it out. I got to think about what I want to build. I haven't decided yet. I get a lot of questions around, so I don't know if people know, but the Unreal Engine has an ONNX Runtime, has a neural network engine plugin that leverages ONNX Runtime. And I get a lot of questions on that one around on-device training. And so once this is in the newest version of that, I'm curious how that will do and what people will do there, because there's some really neat use cases in kind of like the gaming and scenarios. So thanks so much, and we'll see you next time. Everyone else, you can still hang out. We're going to look at some prompt flow fun. So thanks so much, Pedro.
Thank you. Bye, Cassie. Bye, viewers.
Bye. Cool. So we went over a lot there. I think just if there was things you didn't understand, don't worry about it. Just jump into the examples and start pulling it apart. That's the best way to learn. And we provided that link for you so you can go and try it out. Now, for the rest of the time, let me share my screen, because if you tuned in, I think it was last week when we talked about the Llama model 2 in Azure, and we looked at the prompt flow implementation of it. And I went over it pretty quick, and I kind of wanted to go through some of the details on some of those steps that I think would be helpful, because I did get some people asking more questions about it. And I think it's just a really neat project that we could dive into with a little extra time, which we have. We have about 15 minutes here. So let me share my screen. Oh, I just saw another comment here. This is very true. Also, it makes a lot of sense to do on device to avoid unnecessary and costly network traffic. That's right. So it's cheaper to do on device training, right? Because you're using the resources that are local. It's faster. The main limitation is just the size of the models and what you're able to do with the local resources on the device. So those are kind of the trade-offs, but there's a lot of really smart ways that you can do that. Okay, let me get my screen share. There it is. And add that in. Cool. Can you see that? I think that seems a little small. Let me try to make this a little bit bigger. There we go. I think that's good. Okay. So if you missed it last week, we talked about the Llama model, as I was saying, and the way that you can use prompt flow, which is a tool within Azure Machine Learning to create prompts and work with large language models. It does a lot more than that, but at a high level, that's what it is. And so on the right here, you see the prompt flow that we created for inferencing with the Llama model. And then on the left here, you can see more information on the different tooling. I think I need to make this a little bit smaller so I can see it. Hopefully you all can still see it when I do that. But one of the really interesting parts, I think, well, all of it's really cool, to be honest, what you can do. And if we look at the chat window, you can see what this application does is you can ask questions, and then it's going to give me information. This is around a manufacturing retail store. It's kind of the scenario. So helping customers ask questions there. So one of the first things that happens in this particular flow is we do a question embedding. And I kind of want to jump into, I think it's really interesting, and maybe people already are familiar with this, but if you're not really familiar with natural language processing and how we take words and create these embeddings, I think it's really interesting to pull it apart and understand it better, and how we get from point A to point B, because I think a lot of times that's kind of skipped over. And yeah, so let's jump into a little bit of that piece. So for this particular model, what it's doing in the question embedding, it's using cognitive search. and it's taking in a question and it's using the OpenAI embedding model in order to create the output. And then we're using the cognitive search embedding search client in order to then search our database and give back information that is relevant to the retail store that we can then inject in our prompt. Okay, so that's kind of what's happening here. And I want to talk about the embedding. So I'm going to jump way back to a tutorial that I wrote in, I think, 2019. But one thing I like about it is makes it really simple about how we go from words to numbers, and how kind of like these vectorizations and these tokenization things happen. And so what this is, at high level, this is a classification for wine quality on a data set that takes in a description, and it's using classical machine learning. It's a scikit-learn model. So very, very basic, which is why I was older. But what I like about it is it really shows how you go from words to numbers. So in scikit-learn, you have something called the count vectorizer, and you send in all your text and you get all this information about how you want to convert that data or that text into a vector. And here, if we take a look at this one, what I told it is I only wanted a max features of 5. So what it tells it is out of all this text, I want you to tell me the top 5 words, and those are the only words I care about. So everything else will be ignored. If it's not a feature, if the token or the text gram is not in that data set, it's going to be ignored. So this would not create a good result, by the way. 5 features is not a good, but the reason I did that was in this particular tutorial is to really show, okay, this one I can make a little bigger. There we go. To really show what's happening. So I take in, I create that vectorizer based on the description, right? And I say take only the top 5. So these were the top 5 words in there. So these are my only words that this is going to understand. And now if I take a look at the first sentence, this is the representation of this sentence down here, okay? And because it's only going to look at those 5 words, right? These ones that are underlined, those are the only words that would get sent into our machine learning model. So what this basically means is this is the vector representation of this sentence for this data. So 1 means it exists and 0 means it doesn't. So if you take a look, you can see aromas exist, flavors doesn't, fruit, right? And then if we keep going down, palate exists, right? So it's 1, and then wine doesn't, so it's a 0. So I like that because I feel like it really simplifies and helps you understand how we go from words to text to tokens or vectors, and then that's how our machine learning models work. Okay, so that was a very simple count vectorization from a scikit-learn. So now let's go up a level because we're going to get to the large language embeddings. That's where we're going to go. So if we then take a look, I like this blog post that I found where they show different ways to tokenize. So when we're tokenizing words, it's very similar, turning text into numbers. But instead of just like 0, 1 exists, doesn't exist from a vector, from the vectorization that we created, they're actually numeric representations. So we take this large text, and whatever this tokenization understands, it's going to represent that as a number. So we send in a sentence and we get back tokens that represent each character or each token in that sentence, right? So we're still not going from words to numbers, but with large language models, and we need to then go to the embedding. So we need to go from tokenization to a word embedding or vector embedding. And how that happens is we take in those tokens and there's models that are embedding models. Okay, so now I'm going to jump back to my vector search here. And we're going to talk about the embedding models. So we are in this example, we are using this OpenAI model, which is an embedding model, which is going to take in that tokenization and create the embedding, which we're then going to use to retrieve our documents. So I hope that's kind of helpful to think about it really simply and then kind of go right into the complexity. But I like to think about it that way because it helps kind of break down what's happening. Otherwise, it just seems like magic. Which it is cool. Not gonna lie. But when you start thinking about how those pieces come together and how you go from words to tokens to embeddings, then it starts to make sense, I think. So if we take a look at this question embedding, right, we're having our text input and we're creating our embedding. And if I go to vector search, this is what we're using in this prompt flow. So we created a service that is an Azure Cognitive Search service that is for vector search. So if we go into a little bit more detail on vectors and why we use them. So vectors are, and feel free, anybody, if you have questions as I'm going, please put them in the chat. I'm taking a look here. I will definitely answer any questions you have around this as we go. So now that we have kind of that basic understanding of how we're getting from text to vectors, let's talk about why that's important for large language models. So large language models are trained obviously on like huge amounts of data from a certain time. Like I think the ChatGPT was trained in, I think, data up to 2021. But there's reasons that you want your model to understand your own data or more up-to-date data and that type of thing. And that's where this retrieval augmented generation comes in, or RAG for short. And so we want to use that in order to inject information, like basically teach our model more information that it doesn't have to then better answer our questions. And so when what we're doing in this particular flow here is what we are using this cognitive search database, which has the documents for this fictional retail company that have been indexed in a vector database. And so when we get with that same embedding model, and so we get that embedding back from our question, and then we are able to send that into our cognitive search vector database to then put that into the prompt that we're going to give to the Llama model. So that's what we're kind of coming back to, right? And if we take a look at the documentation for the vector search, it's relatively new. I think, what did it say? It's in public preview. Yeah, it's public preview currently. And next week, we're actually going to go into much more detail about how the vector search works in cognitive search. So I'm super excited for that because I think it's super interesting. And yeah, so this goes over kind of limitations, why you would use it, what are the scenarios, that type of thing, and then how you create your embeddings. So if you want to learn how to use this, check out these documentation sites. This is all under the cognitive search documentation, and then under the vectors and vector search. And so here you can see that we're using, where it's saying how we use that same model. This is that OpenAI model in order to create the embeddings of the text. And you can see step by step here how to create that. So the other thing that I think is interesting is I found this other blog about vectors and kind of how they or about embeddings and how they come together, and how, like in vector space, they understand semantic information through semantic similarity based on the embeddings themselves. So if you take a look here, you can see, like in vector space, when they're closer together, they're more similar, right? So that's kind of what those representations mean. And so I think that's another good place to check out and read more and learn about how the vector search works and how those embeddings are created. So I think that's kind of like high level what I wanted to show there about the cognitive search, the vector embedding, and then how we're getting back that result in order to go into our prompt and prompt flow. And then from there, the rest of this is, I talked a little bit high level last week, but we're getting customer information, which we're going to inject into our prompt. And basically all of these steps up here are getting all this information so that we can send it to the Llama model so that it can give a good result in our chat, right? That's the whole thing. We're prompt engineering. We're creating a prompt that's going to give us the best result and what we're looking for our helpful bot here. Okay, ooh, we have a good question here. So let me show this. They're asking, what are the embedding models available in Azure ML, and how do we know whether the embedding model is accurate? So let me take a look. I think that the embedding models for vector search are all OpenAI models. If I am correct, I think I'm correct. But that is a really good question for next week too, when we have the PM for vector search hanging out with us. But let me double check, because I thought I read in here that one of the limitations, let's see. So it doesn't generate vector embeddings for your contract. You need to provide an embedding yourself using the OpenAI, a set service as OpenAI. So let's look at how to generate the embeddings here. So this is where, when you're creating that, you're giving it the engine yourself of the API base that is the embedding. So I haven't tried this out outside of the OpenAI models, but I'm wondering if you had your own embedding model, you could probably use that, although this is all OpenAI, so maybe you couldn't. Come back next week and ask that question again, because I don't know if I'm going to give you the best answer. So really good question. But right now I know that it is the OpenAI models that are supported for sure. And then beyond that, I'm not sure. And then for the correctness of it, when you do the embedding, when you create your vector search embedding and you give the model, how you know it's correct is you use the same exact model when you call or when you create the vector embedding of the question itself. So I know it's correct because if you look here, I am using the same model, the same embedding model as I used on my data. So it's going to be the same vector embedding is going to be the same one that I used on my document. And that's how you know that they're the same and that they're accurate. And if you, so how this works in Azure Machine Learning and in Prompt Flow, if I go back to, let me go to the connections here, you can see that wait, where is it? That's not where I wanted to go, was it? Deployment name. Okay, yeah, so this is an endpoint that I've deployed here that I'm then calling from this connection. Oh, okay, yeah, here it is. So here's my OpenAI, Azure OpenAI connection. Okay, so I wasn't in the right spot, which is right here, which is a endpoint that I have deployed and can then call for the embedding data. So you want to use the same one that you use to create your vector database. You want to use that same one when you're sending in text representation in order to get the embedding in order to get the information back. So good question. But I'm going to ask next week, what are the different models we can use? Because I've really only looked at the OpenAI ones. And I don't know if that's the only one that's supported for cognitive search. That is a fantastic question. We will find out next week. Okay, so then from there, we're taking that and we're just calling out to our search, and then we're getting back our results. And this is going to give me text from my vector database that will help support the context of what I am asking. Okay, and so from there, the other thing I'm doing here is just a customer lookup, so I can get customer information personalized, and I can give all that information to my prompt as well using a Cosmos database. And then here I'm formatting history so that I can continue and have context for other questions as we continue through the chat. I'm going to include all of that in my prompt. So if there's additional context that has already been talked about with the bot, we're going to add that in. And from there, we're going to create the prompt. We simply create the prompt. And here you can see that we're adding in that documentation and the purchases information. So when we called out to the customer API to know what they've purchased previously to see if that can help inform or will help the model perform better. And then the conversation. And so if we look at the output of this prompt, we can see this is all the data that will be sent. Okay. And then from there, we call the Llama model to get the response. And so one thing I want to show you, oh, we are almost out of time. Shoot. Okay. Well, I was going to show you quick what that looks like. Let me see if I can do it in 1 minute. So this is my Llama deployment that I've deployed from the model catalog, where we have all different types of models you can choose from. And this is the Llama endpoint completion, and I'm able to test it. So this is part of my endpoints in Azure Machine Learning. And what I've done is I've taken the prompt that we have created, and I'm just going to paste it in here. And this has all of that you just saw how we put all this together. So this is what actually is getting sent to the Llama model. There's our input string with the information about the product, the different user information as well, so we can be more specific, our temperature, and all the other kind of parameters so it understands how to respond. So when I click test, we'll get back results. And this is a completion. So we're going to get what we sent in, and then we're going to get the answer. So you'll see a bunch of text here, but at the end, you'll see the answer. So if we go back to the parse response, we then split out what the assistant said, and then that is what gives us our result here. Cool. So that's kind of high level of what is happening there and how those come together, and a little bit more about how the vector embeddings are happening, how we get from text to tokens to embeddings, what that actually means, the vocabulary that we give, all that types of stuff. So all those things kind of come together, and that's how it works. And I think it's interesting when you start thinking about it that way, because it starts to kind of pull the curtain off from the magic. Okay, so let me stop sharing my screen here and say goodbye. Thank you for hanging out. Come around next week where we are going to be talking about vector databases with Azure Cognitive Search with the PM. So all those good questions that you have, that you're thinking about, you have a full week to really dive in and come back and learn more and ask us all the things. So thanks, and have a great rest of your day.